Okay, are you ready to talk about part 1C of the program, of the project? Ready to take another delicious bite of the elephant? I can't believe I told that story on the previous video. Alright, well part 1C is basically just a mashup. Take the code that you got from part 1A and take the code you got from part B and put them together. It's not quite that clean, but you're not going to be writing very much code from scratch in part 1C. Alright, basically in this problem what I'm doing is I'm saying I'm going to give you a latitude and a longitude of a station, or I've given you a city and you can look up the latitude and longitude. I'm saying I'm giving you the elevation angle and the azimuth angle of a panel, and I'm giving you the Julian day, we'll say 180. From that, compute the flux of radiation on the panel at every time of the day. Okay, not just at the time, at one particular time, but for every one of those, whatever it works out to, 1,441 times, what was the flux of radiation on the panel? Okay, you already have calculations that when you have an elevation angle and an azimuth of the angle of the sun, what is the energy on the panel, the power on the panel? What you have already is a program that computes the solar elevation angle and the azimuth angle at any given time. You're basically just putting these two things together. Now, I give you a lot of what you need on that manageable steps page. I do want to highlight, I do give you one more thing that I want you to do. I want you to also take the integral of that. The integral of that power on the station over the course of the day gives you the total energy per square meter that fell on that panel. But that's just one line. That's that trap Z, where you give it, trap Z and then the times, and you give it the instantaneous flux. It'll do a trapezoid rule numerical integration. Well, I thought I'd just actually kind of walk you through because it's a little hard to see how these pieces fit together. I mean, let's say I've got part 1 of my project, of project 1Z, let's say step 1 or something. Okay, I'm going to set up my location. I'm going to specify the latitude, the longitude, the offset from UTC, all that kind of stuff. You already had that once before. I think that was in part 2. Part B, I guess we called it. Step 2, compute the solar declination based on the Julian day. Okay, again, you had that already once before. I think it was in, it was in part 1B. Okay, great. Step 3, set up the time array using the code that I gave you earlier. Again, that's literally just cut and pasted from one program to another. Feel free to retype it. It's not that big of a deal. It's 2 lines. However you want to do it. If you want to have 2 windows open, you can be logged into Chesapeake as many times as you want. You want to have 2 windows. One over here is where you're looking at old code, and over here is where you're cutting and pasting the code in. Knock yourself out. It should work just fine. Alright, step 4. Compute the solar elevation and the azimuth for every one of those, whatever it is, 1,441 times. Great. Literally the same as you did before. It's got all that hour angle stuff that I've given you. Once you got that stuff working, just move it on over to the new program. Make a copy of it, move on. Step 5, you're going to compute the solar flux of the atmosphere. This is this S that you had back in part 1A. Okay, where you actually, it was S as a function of time, where time was the Julian day, is equal to, it was the solar constant and then a few terms. Okay, that's the same as you had before too. It's got no problem there. Then, you're going to compute the instantaneous solar flux at every one of those times. Now, we're going to actually have to do this in a loop. So let me show you how, you actually have most of this code before, but now it's going to be inside of a loop. So what you're going to do, for this step 6, let's make like a 6A or something, is what we're going to do is we're going to create a variable that's going to store our instantaneous solar flux, okay? That has the same number of rows and columns as time UTC. What I usually do is I just say like instantaneous solar flux is equal to time UTC. That forces something like Octave to go in and just literally create an array with the same number of rows and columns. I don't care what the values I just put in there. Apparently I've just put times in there, but I don't care. I'm going to clobber every one of those values anyway and replace them with a flux that I'm computing, so what does it matter what those values are? Okay, now we're going to make a loop. So what's going to happen is for every one of those values, for I equals 1 to the number of columns in that array, I can make it the number of, I wrote it here as the number of the columns in TUTC hours, but it could have just easily been instantaneous solar flux, whatever, it would work. Then inside that loop, first, if the solar elevation is positive, compute a transmissivity of the atmosphere, this T atmos. Now, I actually didn't notice this problem with that until I wrote my version of the program. T atmos actually blows up if it gets to be an infinitely large number if the sun angle is below the horizon, or if the sun angle is actually right at the horizon. It just makes a very, very large number. That's mathematically not right. That doesn't make physical sense. The transmissivity of the atmosphere has to be between 0 and 1. So if you go ahead and just sort of set it in a little if statement like this, if the solar elevation at the current time, solar elevation radians time I, is negative, then just set the transmissivity of the Earth's atmosphere to 0. I mean, there's not going to be any radiation anyway, just set it to 0, it's no problem. And then otherwise compute T-atmos. Okay, little hint there, I didn't know that would happen. Inside the loop, you also want to compute zeta, that angular separation between the current position of the sky, of the sun in the sky, its solar elevation and solar azimuth, versus the panel's azimuth and elevation angle. So that's inside that loop as well, because that zeta is changing minute by minute. And then actually compute the instantaneous solar flux at that time. This is this value of S times the transmissivity of the Earth's atmosphere times the cosine of your zeta. If your flux you're going to find out that actually for half the day your flux is negative. The equations are actually not set up to realize the geometry of the situation is it thinks the program is actually thinking, the equations are thinking that a flux of radiation from the sky through the panel is positive, but a flux of radiation from behind the panel through the other way is a negative flux of radiation, which kind of makes some measure of sense, except that doesn't happen, right? The only time the radiation would be coming from behind is at night. Well, there's an Earth in the way. So the equations aren't that smart. So what you're going to have to do is check. If your value you just got for that last minute was, the instantaneous flux was negative, set it to 0, okay? Because the flux will be 0 on the panel. The panel isn't giving off radiation. Well, I mean, it is long-wave radiation, but it isn't giving off power or something. It's just in the darkness. So just set the flux to 0. Then finally, once you have that loop done, it's run for all 1,441 minutes over the course of the day, integrate that instantaneous flux using that trap Z function to get the actual energy per square meter, joules per square meter, that you need at that station. So you'll actually have gotten the total energy that a square meter of that solar panel configured in that way got on that day at that latitude. And at that longitude, how the heck are you going to know if your answer is right? Well, okay, I mean, we can test this. Again, I tested mine using Evansville, Indiana, so go ahead and configure your program, put in the latitude and longitude of Evansville, put in the values of for the panel's configuration that I give you on that manageable steps page in blue line, and put in day 180, and you'll get a graph of this. This is my graph using the plot command. This is my graph of time versus the instantaneous solar flux, and it looks brilliant. I mean, see how the sun comes up around 11 UTC, the sun goes down around 24 UTC on that day. It's just slightly different values than I got before. I'm not sure what's up with that. I might have a different day here. The integral of it, if you get it right, is 2.9 times 10 to the 7th. That should be 10 to the 7th power on that slide right there, not times 107. 10 to the 7th power. Okay, great. What if you don't get it? I've already given you all kinds of examples. Test your solar declination, test to see if it... But honestly, once you get this program together, it's probably going to be fine. How bad is it? Once I deleted the white space in my program and I got rid of the comments, there were 69 working lines in my program. Okay, I'd feel a little bad making you write a program that had 69 lines of Octave when this is really some of your first experiences with Octave. On the other hand, it's almost no new code. You're basically just taking things you already wrote and putting it together. I mean, literally almost every line of the program is either from Part 1A or Part 1B. And so if those programs were working, this is going to be a snap. Alright? What's the deliverable for Part 1C of this program? I want you to modify the program so that it works, but does the calculation for your city rather than for Evansville. And then just submit the program once you have it working and tested and so on. Submit it to me using Turnitin. Okay, Part 1C is the one that kind of makes me a little bit scared. I think from here on out, we're actually just modifying this program in very little ways. By the time you have this program done, your program you have 95% of the code written that you're going to be using. There's just a little bit you're going to be adding or removing from here on out. Okay, please let me know if you have any questions. Don't put this stuff off because it's not going to be something that you can throw together in 20 minutes or something. Please let me know if you have any questions. Dr. John